Hi friends, welcome back to CADable. This is Engineer Ibrahim Omer, and in this tutorial we will solve a truss problem in Ansys. Basically, I have taken this problem from a very famous FEA book by Saeed Moaveni, and it is a chapter 3 problem of truss. So the purpose of this tutorial basically is to compare the results of analytical solutions of FEA with the numerical solution of Ansys. So let's go to the definition of truss. So truss is a structural framework composed of interconnected members, and they are used to support roofs, bridges, and other structures. And they consist of triangular elements connected at the joints. Okay. And what are the assumptions of truss analysis? So the most important assumption is members are connected at their ends by frictionless pins, which means that the members are free to rotate at the joints and there is no bending moments or shear forces in the members. The second assumption is loads are applied only at joints, and the third assumption is self weight of members negligible, and the members are straight, which means that members do not bend or deform under load. Okay, so these are the assumptions of trusses. Let's go to some examples of trusses, and here you can see examples of trusses based on their strength and design. King post truss, queen post, Fink truss, and Pratt truss, Warren truss, flat truss, etc. And let's see some of the real life examples of trusses. The real life examples of trusses include roofs, bridges, transmission towers, tripod stands, wings of airplane, etc. So here I will use this example of truss. It is a very simple truss with the 2 elements and 3 nodes, and I will use this example of truss. I will solve this example in Ansys, and I will compare the results of analytical solution by Saeed Moaveni with the results of Ansys. Okay, basically I will compare these results. Let's say the reaction forces, stresses, deformations, etc. Okay, so let's go to your Ansys. Here you can see that I am using Ansys 18.1, and if you are using a below version of Ansys or a future version of Ansys, you can still follow this tutorial because mostly the commands are same, user interfaces change. So here you can see the analysis types. I'm using let's say this one, static structural, and I will drag this to here. Let's rename this to truss analysis. Here you can see that the Young's modulus, or E, is 10 exponent 6 pounds per inch square, and the cross sectional area is 2.3 inches square. So let's go to Ansys, and I'll go to engineering data, right click and edit. And here you can see I'm using structural steel. One very important thing is you have to correctly put the units. So here you can see my units are in pounds per inch square, and the default units of Ansys are in pascals. So I will change it in PSI, and now I will write 10 exponent 6. Okay, which is basically 1 exponent 7. Here nu, which is the Poisson's ratio, it is not defined because it is not taking any part in this analysis. So it is 0.3, and I will close this window. Now I'll go to your geometry, and here I'm using this one, line bodies. And one very important thing is trusses only carry axial forces, okay, either compression or tension. So it is a 1D problem. So let's go to your geometry and right click, and here you have basically 3 options. Either you can import geometry from any 3D CAD software like SolidWorks, Fusion, Inventor, or CATIA, or you can create your own geometry in Space Plane or Design Modeler. I'm using Design Modeler here. So here you have to set the correct units, and here you can see that the units are in feet, or I can use units in inches, so I will use inches, and I will use 3 into 12, which means this length would be 36 inches. So I'll go to your Ansys, and I'll go to your Design Modeler, I'll go to your units, and I will select this one, inches. Okay, now I'll go to your XY plane, right click and select this one, look at. And here you can see that we have a very simple geometry. We have one element here and we have one element here, and the angles are 60 degrees, and this length is 3 feet, so this length would be 3 feet, and this distance would also be 3 feet, because this is a equilateral triangle. So let's go to our Ansys, and let's go to sketching, line, and here I will draw one line. Okay, and I will draw one line here. Let's go to your dimension, and let's go to your general, and let's say I can define angle. Let's say this angle would also be 60 degree, because if this is 60, this is 60, so this angle would also be 60, because it is a equilateral triangle. Let's go to here details view, and let's say this L1 is 3 into 12, 36 inches, and this L2 is also 36, and this angle is 60 degree. And now I will use this option, zoom to fit. Okay, so geometry is defined, and now I will convert these lines into line body. So let's go to here concept. I will select this option, line from sketches, and base object is this one. I will select apply, and I will click this generate, and now you can see that these lines are basically converted into line body. I'll go to here tree outline, I'll go to here part, and here you can see that my line body. Now I have to define the cross section, and here you can see that the cross sectional area is given. It is 2.3 inch square, but cross section is not given, so I will use circular cross section, and I will use 2.3 inches. Okay, so let's go to here Ansys design modeler, and I'll go to here concept, I'll go to here cross section, I will select this one, circular cross section, and here you can see that I'll go to your details view. You can see that the default radius is 1 inch, and it gives me 3.1416 inches square. So I will do some reverse engineering here, and I will put 2.3 inches square in the calculator, and I will solve for radius, which will give me the 2.3 inches square area. So I will do some simple calculation. So basically I have calculated 2.3 inches square equals to pi r square, and I have calculated the value of r, which is basically 0.85563586678. So I will write this value in the radius, which is 0.855635868. Okay, now this value will give me area of 2.3 inches square, and here you can see that the area is 2.3 inches square, which is same as this area. So I'll go to your line body, I'll go to your details view, and now I will apply the cross section that I have created, the circular cross section of 2.3 inches square. I'll go to here not selected, I'll go to here this drop down, and I will select this one, circular, and I will generate. Now I'll go to your view, and I'll go to here cross section solids, and now you can see that the cross section is applied onto these line bodies. So the geometry step is done, and now I will cancel this. So here you can see that engineering data is done, geometry is done, and now I will apply boundary conditions. So just double click it. Okay, so my geometry is imported that I have just created. Here you can see line body. Basically you can convert this from line body to solids, this one. Okay, now first I will check my material is selected or not. So I'll go to the geometry, line body, and here you can see that material is assigned structural steel. Now I'll go to here mesh, and right click and click here generate mesh. So by default mesh is created, but I don't want this mesh. I want one mesh per element. So I'll go to here mesh, right click, insert, and sizing. And here I will select this one, edge. I will select this edge, hold control, and I will select this edge. I will apply. And I'll go to here element size, and I will select number of divisions, and I will go to here mesh, right click, and update. Now it is divided as number of divisions per element. So basically it is one element and it is one element. So basically we have two elements and we have three nodes. Now I'll go to here analysis settings, and I will turn this weak spring. The purpose of this is to prevent rigid body motions. So I will on this weak spring. Now I will apply boundary conditions. So here you can see that we have fixed support here, we have fixed support here, and we have one load of 200 pounds. So let's go to here analysis, and structural steel, right click, insert, and I will select this one, fixed support. And basically I have to apply this fixed support on this vertex. So I will select vertex and I will select this one. We can call it vertex, point, or node. Basically in FEA we used to call it node, not vertex. So I will apply, and similarly I will apply one fixed support here. So I'll go to a static structural, right click, insert, and I will search for fixed support. I'll go to a vertex and I will select this vertex and I will apply. So now you can see that we have applied the constraints. Now I will apply one load on this vertex. So I'll go to a static structural again, right click, insert, force, and I'll go to a vertex. I will select this vertex, apply, and here I will apply forces in components, not in vectors. So I will change it to components, and here you can see that my forces are applied in the y direction, in the negative y direction, 200 pounds. So here you can see that I have to apply one force here downwards in the negative y. So I'll go to your y component and I will write 200. And here you can see units as well. It is in pound force, which is correct. Basically I have to change the sign. Okay. Now boundary conditions are applied. As you can see that we have two fixed supports and one force here. Now I'll go to a solution and I will solve. So here you can see that there is no error. Now I can find out support reactions, stresses, axial forces, etc. So let's go to here analytical solution, and let's say here we have reaction forces. So I will find definitely reaction forces, and we have stresses. Here you can see these stresses, and here you can see the directional deformation. Basically this U3x and U3y are the deformations of this third node. So I will search for reaction forces, stresses, and deformations. I'll go to Ansys and I will validate this analytical solution with my Ansys solution. Right click, insert, and I will select this one, directional deformation. I will go to geometry. I will select this one, vertex, and I will select this third node and I will apply. And I want directional deformation in x-axis and I want directional deformation in y-axis. So I'll go to your solution phase again, right click, insert, deformation, directional deformation, and I'll go to here geometry and I'll select this one, vertex. I will select this third node again, and this time I will select the y-axis. Okay. Next is I will solve for reaction forces, insert, and I'll go to your probe, force reaction, and I will select this boundary condition, this one. Similarly, solution, insert, probe, force reaction, and now I will select this boundary condition. Okay, and also I want stresses. I'll go to insert and I'll go to here beam tool and I will select this beam tool. So we have minimum combined stress. Let's say I want this direct stress only, so I will delete this one. Okay, and let's say I want to find out force reactions as well, axial forces in these elements. So I'll go to a beam results, I will select this one, axial force, and I will select this element, apply. Similarly, solution, insert, beam results, axial force, and edge, and apply. Okay. Now I will validate my Ansys results with the analytical results of Saeed Moaveni. So right click and I will select this one, evaluate all results. So here you can see the directional deformation in node 3. Ux is 0 and y is negative 2.087 exponent minus 4 inches. Basically this is the deformation of this node. Okay. So basically it is 0 in x direction, and in the y direction we have this displacement. So I'll go to here Ansys, and here you can see the directional deformation. Here I'll go to this one and I will select this option, show undeformed wireframe, and I will select this one, show undeformed model. Okay, so that we can compare these results because this node was just here and now it is here. It is not a correct scale, but it will give you a very better visualization. So here you can see the directional deformation in x-axis is approximately 0 because 3.810 exponent minus 20 is a very small number, so it is correct. Okay, and now the deformation in y direction is minus 2.087 exponent minus 4 inches. So I'll go to here Ansys, I'll go to here directional deformation 2, which is basically in y-axis, and here you can see minus 2.087 exponent minus 4 inches, which is correct. Here we can animate our results as well. Okay, and now I will let's say validate the reaction forces. So basically reaction force is 115.5, and when we resolve this reaction forces into its components, so we will find the reaction forces 57.73 pounds and 100 pounds. So I'll go to here Ansys and I'll go to here force reaction. So here you can see the reaction forces are same, 57.605, and here we have reaction force 57.73, which is approximately same. And here we have 100 pounds and here we have also 100 pounds. Similarly, this second reaction, we have this one, minus 57.605 and 100. So here we have a negative sign. Let's go to here Ansys, and here you can see we have negative. Okay, this one negative and this one is positive. So it is validated, and now I will let's say validate this stress result. It is minus 50.205 in compression. So I'll go to here Ansys and I'll go to here direct stress. So here in Ansys we have stress minus 50.215, and here in Saeed Moaveni we have minus 50.205. So here we can compute the error percentage, or we can compute the accuracy of this Ansys result. So I'll go to here calculator and I will write 50.205 of analytical solution is divided by 50.215 of Ansys. So here you can see that results are 0.999% accurate. Okay, in general, if the results are 98% accurate, so we will go with the Ansys results. And here we have validated directional deformation, stresses and force reaction in Ansys. Also we can find out the axial forces. It is 115.41 and it is also 115.41. So here you can also validate this one. This one 115.5 pounds, and in Ansys we have 115.41. So it is also approximately same. Lastly, I will let's say find out total deformation as well. So you can see different contours, solution, evaluate all results, and here you can see the total deformation. So in this tutorial, basically we have validated the analytical results of Saeed Moaveni with the FEA solution. I hope you have learned something new. I hope you like it. If you have any questions, any queries related to this tutorial or any other tutorial in my list, you can ask in comment section. Thanks for watching, and please subscribe to our channel for more informative and interesting projects. Thank you.